Hello everybody, this is John Buck back with another continuous time linear systems video. And in today's video we're going to talk about the convolution integral, how we can interpret it graphically, and then do an example of computing a convolution of two continuous time signals. So I've written the convolution integral we found in the last video here in a colorful way so that we can emphasize where each piece of this comes from, because there's really, in order to interpret these graphically, there's really three main steps we need to repeat or to perform, and then we need to repeat these steps several times as we move through different regions of the signal. So to break these down one at a time, let's start with the blue thing. The blue thing says that we're looking at h of t minus tau, but we're integrating it as a function of tau. So for the first thing is we can think of this as a flip and a shift, like we saw in discrete time. We could rewrite this as h of minus tau minus t, right? So in terms of treating tau as the independent variable, this is like we first flip the signal and then shift right. After we flipped it, we shift right by t, which is the current time we want to find the output for. So let's put that down in blue first. So we flip h of tau, then we delay it or shift right by t. So that's what the blue part says. And then the next thing we do is we multiply that with x of tau. So we form a product So we multiply the input signal x of tau with h of t minus tau, this flipped and shifted version, to get the product of the two. Right, so we'll have a new signal. That's what we get from multiplying these other two signals together. And then once we have that new product signal, we integrate it, which is to find the area under the curve over all tau. Right, so we look at that product signal for a particular value of little t, or for t, the time, and we integrate that so we can find that's finding the area under the curve. And that gives us one value at that one time t. Now to find this overall for a general signal, it turns out that we have to develop some talent at breaking the signals and the shifts into different regions. We need to recognize when we move into different regions, when things start overlapping, or maybe different parts of one of the signals starts overlapping another, to change the product in some form. And then for each region, we're going to come up with an equation for y of t. So let's move on to the next page, and I'll show you what I mean by that. Okay, so in this example, I'm going to convolve h of t that looks like this, which is a pulse of height 1 from time 0 to 4, with x of t being the unit step. So this has height 1 for all time. And so I'm going to implement the convolution integral like we talked about on the last page. I'm going to write this as x of tau and then have a flipped and shifted version of h of tau. So let me start by drawing those. All right, so now I have my x of tau and h of minus tau, and I think about, I'm going to start taking x or h of minus tau here and sliding it around, right, of moving it. But in order to do that, I think I can do it cleverly here. Right, so if I select this, I can think about what will happen in these different regions as I think about different shifts, right? If I shift negatively, so if my t is negative time, I'm going to move it over here, and when I multiply these two signals together vertically, I'll get 0, right? Because neither of them overlap. So that's my first region. And then as I move to the right, as t increases, I'm shifting this more and more to the right, I'll see these things overlapping, and I can compute a product for that. Will have one form. And then the other change that happens is once I've moved this far enough to the right, that the h of minus tau gets completely inside x of tau. Right, because then I'll have a product of the two, but once I get beyond that, nothing's really changing in terms of the area of the overlapping signal. So let me put this back, and let's write down those three regions. That's always a good thing to think about when I've flipped things over, especially for simple signals. I'm going to have three regions where I need to evaluate this integral with slightly different approaches. The one will be very easy. So when t is less than 0, as t goes from 0 to 4, well, this is really not the right place to put this. Let me finish writing it, and then I'll move it. And then the third case will be when t is greater than 4. All right, so these are going to be my three regions as I think about sliding them through. I'm going to maybe just do each one on a separate page. Okay, so let me set up a new page for the t less than 0 case. All right, so for the first region here, I've shown this. Now I've got h of minus tau minus a minus 1. That is, I've shifted it 1 to the left so that the what was the original origin here, let me show that clearly, lines up right under minus 1. Well, it lines up better than I drew it. But it lines up right under minus 1. So when I multiply these two together, when I look at this and multiply for each point in time, I multiply straight up and down, I'll see that x of tau, h of t minus tau, which is what I have here, equals 0 if t is less than 0, right? If I've shifted it all to the left, the pulse doesn't overlap at all with the unit step. And so that tells me that when I do the output, the integral of y of t from minus infinity to infinity of x of tau, h of t minus tau, this integral can be simplified when t is less than 0 because the integrand will be 0. Right, so this makes us a very simple, happy integral, easy integral to do. Oh, not that. I want this. So I can scroll up a little bit. Because the area under the curve for all time of 0 is pretty simply 0. So this tells me that y of t equals 0 for t less than 0, when the two things don't overlap. So that's the first region. Let's move on to the second region. So now in this region, this is the region where between 0 and 4 is when this pulse partly overlaps the edge here. So there is some non-trivial overlap, but it's not the whole way in. The pulse is not the whole way inside the unit step yet. So as I've drawn it here, we could look and say, well, this looks like about time 2 because the 0 here lines up with time 2 above, right? So this would be for this particular picture drawing this. But we can say when I do this, the integral for I'm going to have the integral of this product for tau, but it's only going to be non-zero between when tau goes from 0 up until t. Right, this point here is at t, right, is the point at which, more generally, is the point at which when tau grows greater than t, right? Because in the general case, this is h of t minus tau. So as tau increases, this thing gets smaller and smaller until it hits 0 here at this edge, right? So that's the last value of tau allowed to be non-zero. So again, the next step is to write the product function. We would say that x of tau times h of t minus tau in this region is equal to, well, 1 times 1 as long as tau goes from 0 to t, right? So if that's the case, we can say that the integral from minus infinity to infinity of x of tau, h of t minus tau, d tau, will be the integral. And now we use this to change the limits. This tells us that it's anywhere outside of this region, I guess I forgot to say, it's 0 otherwise. So that simplifies the integral. Rather than breaking the integral into pieces, we know all those other pieces are 0, and we only need to integrate from 0 to t here. And in that region, it's 1 d tau. And so that becomes a very simple integral, that it's tau evaluated between 0 and t, which is t minus 0. So from 0 to 4, y of t is just going to be equal to t in this region. So it's going to be 0 up first and then start ramping up. So maybe I should start collecting those all together on a new page, my different values of y. Okay, so as I start to collect this is what the region 1, I found that it's 0. For the second region, it's equal to t from 0 to 4. And now we have to go back and do the third region for t greater than 4. Okay, so region 4 is the region where t is greater than or equal to 4. And so again, I've still got my x of tau. And then here's my h of minus tau minus t plotted as a function of tau, right? So this right edge was when tau equals t. The argument of this will be 0. And the left edge is when tau equals t minus 4. These all cancel out, and I'm left with 4. So this is the flipped and shifted version of h of t. And so why we have a new region is here. What has changed is that my product function will be different because this pulse is completely inside the unit step. Right? So this is my first step. I flipped and shifted into the region, and now I need to find the product function. So when I look in this region, I'll have x of tau, h of, if I write it out this way, minus of tau minus t will be just this rectangle here. Oh, that's a terrible rectangle. Oops. Stop. Right, so this is my product function. It has height 1 because I have 1 times 1 up here going from t minus 4 to t everywhere. So this is my product function. So my y in this region, y of t, is the area under this thing, right? This is the third step of ours. Staying with my colors thing, this would be the green step. And so the area under that curve, well, it's 4 wide and 1 tall, right? Or I could do, if I want to do it out more carefully, I could write the integral. Right, we're saying I can write the product function as 1 within these regions and 0 everywhere else. So the integral from minus infinity to plus infinity, I get to shorten the limits effectively. And so this would have given me tau, if I did it out the long way, with the limits of t and t minus 4. So I get t minus 4, which gives me 4 back again. Right, so this is my, for my third region, this is what it looks like. So let me go add that to my other page. So here on my last page where I'm saving up all the results, I now have my third region, which says y of t equals 4 when t is greater than or equal to 4. So I've finished my 3 regions, and I can sketch the function. Right, so when I draw, this is now back to being y of t. When I plot this function, it's 0 up until time 0, the blue line here, and then above from 0 to 4 it has slope 1, which is t, and then everything beyond that it's 4. So this is the convolution of that pulse with the unit step. Okay, so that's a convolution example, breaking it down step by step for you and putting them all together and showing how we have to, the key idea is you flip one of the terms, it can be either one. In this example, we were always flipping h, but we flip something, then we shift it. Once we've shifted it, we find the product function by multiplying the two things together at every point in time, and then we find the area under that product function, sometimes as a function of t, how much we shifted it by, as in this example. But at the beginning and the end, we had constants. So you get lots of chances to practice this in class problems, tutorials, homework. But I'm going to stop here for this video and upload it. And we'll get more practice with convolution in class later this week.